want to try to simplify some radicals here. And the process that I like to use in doing that is, one, get my head on straight. I'm looking for perfect squares, but not with constants, but with variables raised to an exponent. So the first thing I'm going to do is I'm going to rewrite some of these bases into perfect squares. So x to the fifth is not a perfect square, but I know x to the fourth is, and I have one more x there. So x to the fifth can be rewritten as factors x to the fourth times x. And I know x to the fourth is my highest perfect square. Now, what about y to the 13th? I want to rewrite that as factors, where one factor is the highest perfect square. So what does that become? That's y to the 12th. And then I have one y left over. Y to the 12th times y to the first. When multiplying like bases, you add the exponents. That's y to the 13th. And then z to the 7th. What's its highest perfect square that I can factor out? Well, that's z to the 6th, then times a z. From here, what I'm allowed to do then is break apart the different roots. So I really have the square root of x to the 4th times the square root of x times the square root of y to the 12th times the square root of y times the square root of z to the 6th times the square root of z. Now I did that for a reason, because I now can pull out the perfect square of x to the 4th. What times what makes x to the 4th? And x squared does. Square root of x, there's no perfect squares within that x. So that will remain underneath the radical. The next one is the square root of y to the 12th. That's y to the 6th. Square root of y remains square root of y. So I'll put that back underneath the root. The square root of z to the 6th, what times what makes z to the 6th? A z to the cube does. And then I have remaining square root of z left. So in that process right there, I was able to look at each of the bases and refactor them or factor them into perfect squares.